In this video, I'm going to go over a few examples that use the first and second derivative to investigate the properties of the graph of a function. Okay, so this first example says to sketch a graph that has the following properties, and then it lists a few different traits based on the first and second derivative. Let's go through each of these to see what these can tell us. So the first one says f prime of -1 and f prime of 1 is equal to 0. So whenever the derivative is equal to 0, that means those values of x represent critical points. So we're going to have critical points at x is equal to -1 and +1. And again, a critical point just means the derivative is equal to 0. On the graph, this means that the tangent line has a slope of 0 or the tangent line is horizontal. We can think of it either of those ways. Next up, we have the statement the first derivative of x is greater than 0 or it's positive on both of these intervals. That just means that the function is increasing over these intervals. Similarly, f prime of x is less than 0 on the interval -1 to 1. This means the function is decreasing in this interval. And then looking at the second derivative tells us about concavity. So when the second derivative is negative, that means the function is concave down. And inversely, when the second derivative is positive, this means the function is concave up. Okay, so let's try to put all this together and see if we can come up with what a graph might look like. Now, there's more than one option. There's probably an infinite number of options for what this graph could look like. So it seems like things are changing between -1 or at -1 and +1. That's where the function goes from increasing to decreasing and then back to increasing. So we also have critical points at -1 and 1. So all of these values that are listed here correspond to the x-coordinates, so we don't know what the y-coordinates are, so it doesn't really matter where on the y-scale we graph things. So I'll just start at the top of the list. So we have critical points at -1 and +1. This means that we have a horizontal tangent line at both of these points. So if we have a critical value at -1, that means we're going to have the slope of the tangent line is going to be horizontal, or 0, which means it'll be horizontal. And also at -1, we're going to the left of -1, from -infinity, we're increasing. So looks like the graph is going to do something like this. So in this interval from -infinity to -1, the function will be increasing. Then it looks like it's going to be increasing again from 1 to infinity. Down here, we're decreasing from -1 to +1. So it looks like the function is going to be decreasing down to 1. And then we have another critical point at +1. So the graph is going to level off again. And then it starts to increase again. So it's going to start to do something like this. Next up, we have some information about concavity. So from -infinity to 0, the function is concave down. And then it looks like at 0, the function becomes concave up. So that's essentially what's happening in this area right here. That looks like an inflection point. So just kind of going through again, we have critical points at -1 and +1. That's where the function has a horizontal tangent line. We have the correct intervals where the function is increasing from -infinity to -1 and +1 to +infinity. We're decreasing in between there, and then our concavity lines up with what we have. So our graph is going to look something like this. So it looks like it's a cubic, could be a cubic function. And again, this could be kind of anywhere along the y-axis because we don't have any information about the y values here. All right, for this next example, it says For the following functions, find the intervals of increasing and decreasing, all local extrema, intervals of concavity, and the inflection points. So we're going to look at two different functions. The first function we're going to have is f of x is equal to x cubed plus x to the fourth. So to find all of this information, we need to find both the first derivative and the second derivative. So the first derivative, we're just going to use the power rule for both terms. So we're going to end up with 3x squared plus 4x cubed. Then finding the second derivative, we're going to have f double prime of x, again using the power rule on both terms. We have 6x plus 12x squared. Okay, so let's look at what the first derivative can tell us. The first derivative can tell us where the function is increasing and decreasing, help us find local extrema. And to do that, we take the first derivative and we set it equal to 0 and solve. I'm going to factor out an x squared. I'm left with 3 plus 4x is equal to 0. So when x squared is equal to 0, that means x is going to be equal to 0. And then when 3 plus 4x is equal to 0, we're going to have negative 3/4. So on our number line, we're going to separate the intervals at 0 and at negative 3/4. And then we want to test values inside each of these intervals. And to be clear, we want to test in the first derivative. We want to see where is the first derivative positive, where is the first derivative negative. So sometimes I can write my numbers in order here. Let's try that again. Negative 3/4 on the left, and then 0 right here. Okay, so testing a number to the left of negative 3/4, I don't know, how about negative 10? So substituting that in over here, negative 10 cubed is negative 1,000 times 4 is negative 4,000. That'll keep the first derivative negative. So this will be negative interval here. A value to test between negative 3/4 and 0 might be negative 1/2. Substituting that in, well, negative 1/2 squared is going to be positive 1/4 times 3 is 3/4. And then negative 1/2 to the third is negative 1/8. Negative 1/8 times 4 is negative 1/4. So that value is 2/4. We don't really care about what that value is, we just care what the sign is, and that's going to be a positive value. And then selecting a value to the right of 0 in this third interval, I don't know, how about 1? When I input 1 in here, well, everything's going to be positive, so this will be a positive interval. Okay, so let's see what's happening here. We need to figure out where this function is increasing and decreasing. The intervals where we get negative values tell us where the function is decreasing. So we're going to be decreasing in this interval, and then in both of these intervals, we're going to be increasing. So what we see is at 0, this is a critical point because the function, or the derivative of the function is equal to 0 at that point, but it's not changing from positive to negative or negative to positive. So that just means at 0, this is not a local extrema. Okay, so that's what's happening when we look at the first derivative. Let's now look at the second derivative, and it's the same idea. We want to take the second derivative, 6x plus 12x squared, set that equal to 0. I'm going to factor out a 6x. I'm left with 1 plus 2x. That's equal to 0. So we end up with x is equal to 0 and x is equal to negative 1/2. Let's put these values on a number line. Let's see if I can put things in the correct order this time. Okay, and same thing. We want to pick values inside each of these intervals and test this time in the second derivative. To the left of negative 1/2, how about negative 1? Plugging in negative 1, well, negative 1 squared is positive 1 times 12 is 12. Plus 6 times negative 1 is still a positive value, so this will be positive here. Between negative 1 and 0, I guess I'll test negative 1/4. Negative 1/4 squared is positive 1/2 times 12 is positive 6. And then, hang on, is that right? It's actually not right. When I do negative 1/4 in for x, negative 1/4 squared is not 1/2, it's 1/16. So 1/16 times 12, I get 12/16, which is 3/4. And then substituting in negative 1/4 into this term, negative 1/4 times 6 is going to be negative 6/4. So negative 6/4 plus 3/4 is negative 3/4, which is a negative value. And then choosing a value in the rightmost interval, so anything to the right of 1 or 0, we can do 1. Again, every term is positive, so this will end up being positive in this interval. So again, when we look at the second derivative, the sign of the intervals for the second derivative tells us whether we're concave up or concave down. So in this interval, we're going to be concave up. Here we'll be down, and then we go back to up. And again, anytime there's a change in concavity, that means where the concavity changes, that's where we have an inflection point. So we're going to have an inflection point at negative 1/2 and positive 0. All right, so let's put it all together here. So we'll say we have an increasing interval, or an interval with increasing values. We're going to say from negative 3/4 to 0. The function is decreasing on the interval negative infinity to negative 3/4. Sorry, for the increasing it should be negative 3/4 to infinity, all the way to the right. We have a local min value at negative 3/4. That's where the function goes from decreasing to increasing. So we have a local min at x is equal to negative 3/4. There's no local max here because there's nowhere where the function goes from increasing to decreasing. So we could add that, no local max. Let's look at our concavity. We're concave up in the intervals, let's see, negative infinity to negative 1/2, and so union 0 to positive infinity. The function is concave down in between those two values, or those two intervals, so negative 1/2 to 0. And then lastly, we want to look at the inflection points. We said there's two inflection points, negative 1/2 and 0. Those are the x values. So the inflection points, to find the ordered pairs, we just take the inflection points, so negative 1/2, and we're going to input that into the original function. So negative 1/2 and negative 1/16, and then we input 0, we get 0. So 0, 0 for the inflection points. So in questions like this, it's probably a good idea to actually graph the original function, see if everything lines up. I did that separately. I'm not going to show the graph here in this video, but by doing so, you could verify that we have all of these intervals correct, we have the correct inflection points, and then the local min is correct. All right, let's do one last example. Same prompt, we just have a different function, and that function is g of x is equal to x plus sine of x. Actually, it's going to be sine of 2x here. This is going to be on the interval negative pi over 2 to pi over 2. So if you think about the unit circle, that's from down at the bottom of the unit circle up to the top, and quadrant 4 and quadrant 1 is what we're going to be working on here. So everything is going to be quite the same as the last example. The only difference here is the function is going to be a little bit more complicated. So solving the equations when the first derivative is equal to 0 and the second derivative is equal to 0 is going to be just a little bit more work. So finding the first derivative, g prime of x, is going to be 1 plus the derivative of sine is cosine. So using the chain rule, this is what we're going to get for the first derivative. I'm just going to work with the first derivative first here, and then we'll move on to the second derivative. So we want to set this equal to 0. So we have 0 is equal to 1 plus 2 cosine of 2x. Subtract 1 and divide by 2. We're going to have negative 1/2 is equal to cosine of 2x. Now, if you can recall how to solve this type of equation, first thing we want to do is we want to say, well, when is cosine equal to negative 1/2? And cosine is equal to negative 1/2 at 2 pi over 3 and 4 pi over 3, so in quadrants 2 and 3. So what we do is we say 2x here is equal to 2 pi over 3 and 4 pi over 3. And what we want to do is we're going to separate these into two separate equations, and we ultimately need to solve for x. So we get 2x is equal to 2 pi over 3 plus 2k pi. And we need to use this general term 2k pi because we have 2x here. And then the second equation is going to be 2x is equal to 4 pi over 3 plus 2k pi. So dividing both sides of each equation by 2, we get x is equal to 2 pi over 6, which is pi over 3, plus 2k pi divided by 2 is k pi. And then in the second equation, we're going to have x is equal to 4 pi over 6, which is 2 pi over 3 plus k times pi. And then what we do is we test values of k, because we ultimately want angles that are in this interval, negative pi over 2 to pi over 2. So when k is equal to 0, we get an x value of x is equal to pi over 3. Pi over 3 is in that interval, so pi over 3 is a solution. When k is equal to 1, well, I get x is equal to pi over 3 plus 3 pi over 3, which is 4 pi over 3, but that is not in the solution, or not in the interval. So that's not a solution here. So it looks like we just have x is equal to pi over 3. We could have also made k negative 1, but if k is negative 1, we're going to get negative 2 pi over 3, which again is not in the interval. So x equals pi over 3 here. That's one of our critical points. And then we're going to do the same thing on the second equation. I should say that k needs to be an integer in this scenario. In this one, I do need to make k equal to negative 1. So when I make k equal to negative 1, I get x is equal to 2 pi over 3 minus 1 pi, so which is negative 3 pi over 3. That gives me negative pi over 3. That is actually in the interval. That would be in quadrant 4. And remember, we're looking at values in quadrant 4, quadrant 1. Just to get a visual, we want values in this area. So negative pi over 3, that's going to work. When k is equal to 0, I get x is equal to 2 pi over 3. That would be a value in quadrant 2. That's not in the interval, so that's a no-go. So our two critical values are negative pi over 3 and pi over 3. Another way of saying negative pi over 3 is, if we're thinking about it visually on the unit circle, that's 5 pi over 3, but we're going to use negative pi over 3 because that's the value in the interval. All right, so those are the two critical values we're going to use, or critical points, I should say. So negative pi over 3 to pi over 3. So we want to test values inside each of these intervals, and again, we're going to test that in the first derivative. So the easiest thing is to test 0. Testing 0, plugging that in for x in this cosine function. Cosine of 0 is 1. 1 times 2 is 2. 2 plus 1 is 3. So that's going to be positive in here. Next, I'll test, how about negative pi? So cosine of 2 times negative pi is cosine of negative 2 pi. It's the same thing as cosine of 2 pi. Cosine of 2 pi is I'm just remembering that we want to stay in this interval here, so we don't actually want to test negative pi. So let's go back here and test something that is actually going to be in the interval. So we want to go down to negative pi over 2. So an angle that is between negative pi over 2 and negative pi over 3. Well, what should we test there? Let's get a common denominator, common denominator of 6. So this is 3 pi over 6. This is negative 2 pi over 6. So we want something in between there. So we want negative 2.5 pi over 6, which is the same as 5 pi over 12 negative. So let's test that value in this interval. That'll be between these two endpoints of that interval. So plugging that into the first derivative, cosine of 2x, so 2 times negative 5 pi over 12 is going to be negative 10 pi over 12, negative 10 pi, negative 10 pi over 12 is the same as negative 5 pi over 6. So cosine of negative 5 pi over 6, well, 5 pi over 6 is in quadrant 2, negative 5 pi over 6 would be quadrant 3, that'll be negative root 3 over 2. Times 2 will be negative root 3, negative root 3 plus 1 will be like negative 0.7, which is a negative value. So we're going to be negative in this interval. So again, kind of a lot of work to figure out the sign in this interval. Okay, and then similar idea, we want a value between pi over 3 and pi over 2. Well, 5 pi over 12 is going to work here. So we want to substitute that into the function, and I'll do this off to the side just to have some more room here. So 1 plus cosine 2 times 5 pi over 12 times 2. 1 plus, again, cosine of 10 pi over 12 is cosine of 5 pi over 6 times 2. Cosine of 5 pi over 6 is root 3 over 2 times 2 plus 1. So that's 1 plus square root 3, and that is definitely a positive value. Sorry, this is negative here, because that's quadrant 2. So this is actually negative, so this will again be negative 0.7 about. So not definitely a positive value, definitely a negative value here. Okay, so a little tedious to find where those intervals are positive and negative. Let me clean up the workspace here. We'll keep what's important, and then we'll look at the second derivative. All right, so we're going to start with the first derivative, which was g prime of x is equal to 1 plus cosine of 2x times 2. I want to take the second derivative of this. Derivative of 1 is just 0. Derivative of cosine is negative sine, and we're going to have a 2. I'm going to rewrite this as 2 cosine of 2x. So the derivative of cosine is negative sine, so we'll have negative 2 sine of 2x. And then we have to use the chain rule, so times 2. We end up with negative 4 sine of 2x for the second derivative. Okay, again, we want to set this second derivative equal to 0. Divide both sides by negative 4, so we get sine of 2x is equal to 0. And again, to solve this equation, we ask ourselves, when is sine equal to 0? Sine is equal to 0 along the x-axis. So sine is equal to 0 at pi and 2 pi. I'm not going to say 2 pi though, I'll say 0. So we set 2x equal to 0 plus 2k pi, and then 2x is equal to pi plus 2k pi. Again, k is an integer here. Solving for x, divide by 2, we get 0 plus k pi. Then we're going to test values for k. When k is equal to 0, I get x is equal to 0. That is in this interval, so we're good there. If k was negative 1, I'd get negative pi. If k is positive 1, I get positive pi. Neither pi nor negative pi are in that interval, so only x is equal to 0 here is the important value here. On the second equation, again, divide by 2, I get x is equal to pi over 2 plus k pi. Let's test some values. If k is equal to negative 1, I get pi over 2 minus pi, which will leave negative pi over 2, which is right on the left edge of the interval. And since it's a closed interval, that value will be included. And then when k is equal to 0, we're going to get x is equal to pi over 2. And that also is a value in the interval. So both of these are going to work in this second equation, as well as x is equal to 0. So let's make a number line plotting these values. Okay, so we want to test values. Because our interval is from negative pi over 2 to pi over 2, we just need to test values in these two intervals here. And I'll test negative pi over 4 and pi over 4. So g double prime of negative pi over 4, we get negative 4 sine, excuse me, 2 times negative pi over 4 is negative pi over 2. Sine at negative pi over 2 is negative 1, so this is positive 4. So we get a positive value in this interval. Similarly, when we input pi over 4 into the second derivative, 2 times positive 4 is positive pi over 2. Sine of pi over 2 is positive 1. So this is negative 4, which is obviously a negative value. So because this is the second derivative, this is telling us what the concavity is. The concavity here is going to be concave up. In this interval, it'll be concave down. And then because the concavity is changing from concave up to concave down, that means that this value is an inflection point. Okay, so summarizing everything we've done on this problem, we saw that we had an increasing interval from negative pi over 3 to pi over 3. We had a decreasing interval. We actually had two of them, negative pi over 2 to negative pi over 3. We're going to include the negative pi over 2 because that value in the interval is a closed interval, and we include that endpoint. And then union pi over 3 to positive pi over 2, like this. We're going to have a local, let's look back here. So at this point, we went from a negative or a decreasing interval to an increasing interval. So that graph does something like this. So that's going to be a local min there. And then when we go from positive to negative, that's when we have a local max. So local min at x is equal to negative pi over 3. Local max at x is equal to positive pi over 3. And then for concavity, we are concave up in the interval negative pi over 2 to 0, and then concave down from 0 to pi over 2. And then lastly, the inflection point. Well, we know the x-coordinate of the inflection point, it was 0. And then to find the y-coordinate, we're going to input the 0 into the function. So sine of 2 times 0, so sine of 0 is 0, plus 0 is 0. So the inflection point here is going to be 0. And then let's actually look at this graph, because this graph is actually kind of interesting. So this was the function, g of x is equal to x plus sine of 2x. So we saw that our interval was from negative pi over 2 to about pi over 2. Okay, and so we said that we're concave up in this interval, and then concave down in this interval. We said we were decreasing from here to negative pi over 3, then increasing from negative pi over 3 to positive pi over 3, and then decreasing again from pi over 3 to pi over 2. We had a local minimum value down here, local max down here, and then this was our inflection point. So everything we found matches up with what we see in the graph.